Hey folks, welcome to this tutorial on unit tests and the builder pattern. We are going to learn how to write validators and verifiers of our data classes and algorithms that can be used with the Juice unit test class and the unit test runner class. So if you'll bear with me, I've got my script over here to make sure I don't get off track and go on a bunch of tangents and whatnot. If you like what you see in this tutorial, I have a modern C++/Juice framework course linked in the description. You can study with me in a mentored one-on-one environment and really take your programming to the next level. All right, with that said, let's answer this question. Why do we want to write unit tests and validators? That's a good question. So we want to write these things because we want to make sure that some fixed input produces the same output when we are developing or revising our algorithms. Let's go through a simple example of that. Let's say we start writing an algorithm that spits out a pair of numbers on either side of whatever input we give it. And those numbers are 1 away from the input. So if we pass in a 1, input, if we pass in an input of 1, we expect to get back a 0 and 2, right? That's a really simple algorithm, okay? We can expect that for an input of 1, we're always going to get back a 0 and a 2. Okay, now just imagine that as time progresses and our algorithm evolves, we start testing with other numbers. All right, we start testing with small inputs, really tiny fractions, really huge monster numbers. And we don't know anymore if when we pass in a 1, we're still going to get back a 0 or a 2. Okay, so we can add a unit test to the beginning of our program that checks this, and if the unit test fails, then we know that we broke our algorithm and we need to fix it. All right, so let's talk about a real-world example of this, because this was, pretty generic. Okay, let's check out a real-world example. All right, I will be using an inspiration from my own personal development hell right now, which is turning MIDI input into a playable guitar tablature. So let me give you a quick look at how that is being used in my app, Chordy app. All right, here's my app, Chordy. So the way my algorithm works is it takes some MIDI input, which can either be from playing a regular MIDI keyboard like that, or clicking on these guys right here like that, or clicking on the notes just directly like that. It takes in that MIDI information, it takes in the neck tuning, that's this part right here, takes in the number of frets, and it spits out a set of playable tab figures that gets displayed on the neck that you can cycle through. So let me show you a little example of this in action. So I'll just click on a triad right here. Let me just do this like a second inversion triad and that sort of thing. So this triad, the notes of this triad exist in 42 possible configurations on the neck. They are all physically playable. All right. So this is basically what my algorithm does. It figures this stuff out. Okay, let me go back to the very beginning so we can see the default choice. Okay, so with that said, let me show you the algorithm in code form so you can see kind of how complex it is and why it's difficult to debug and why it's difficult to revise and why I need a unit test to make sure that with these simple inputs, I still produce output like this, but when I add really complicated inputs with like a bunch of strings and some weird tunings, like how I can change all the tuning and stuff here, when I add that stuff in there, I need to make sure that I still get these types of really simple outputs and that I haven't butchered my algorithm that produces these simple outputs, okay? So let's take a quick look at that. So that's over here in the Fretboard job. So if I go to the run job, because this happens on a background thread, I've got all this counter stuff that's going on. I've got this do work function that gets called. And in that do work function, I go through all of this, basically figure out all the possible ways you can play all these notes on the neck. I check if they, they can be turned into a playable fingering, and then I check if the fingering is actually playable and whatnot. And if it is, then I add it to that set of choices. And if I go back over to here, I'll plug in a new voicing right here, and you'll see it figures out for this set of input right here, there are 216 possibles that it figured out, and it was able to reduce it down to 37, okay? So it's not a simple algorithm, it's got some really complicated stuff, and it's very easy to break. So that's the main reason that I need to have this. So an instance of that is like the make fingering function over here. It does a lot of stuff where it takes the notes as you're playing and it figures out where they are on the neck and if it's like within the range and whatnot, and or if you can bar it with multiple notes and whatnot. It's a pretty good mind bender to try and figure out if it's doing the right thing or not. Okay, so for the purpose of this tutorial, I won't be using that algorithm directly and checking the results of that. It's just too complex for what we're trying to do. What I will do instead is write some dummy classes that approximate the behavior of that in a very simplified way, just to make this tutorial a lot easier to understand. So before we do that, let's go over some of the goals when we write a validator for a unit test that we want to achieve. All right, one goal when designing a validator object is to come up with a syntactic style of expressing the test that is easy to understand. As in, we're gonna have some validator object like that. It's going to take some kind of input, and it's going to have a couple member functions, and each of those member functions will check whether or not some algorithm that used the input produced an expected output value. As in, we could have like, maybe we just name that function has, and it's like, has some value like this. And then we want to be able to chain a couple of them together like that. So we'll, add a couple more like that. Okay. That's an example of like, it's a really clear syntactic style, especially if we start formatting it in a certain way. We can see, we can see that like we've got this input and we hope that our algorithm produces this value and that it has this other value. That's like a good example of a nice syntactic style. All right, so here's an example of what that will actually look like with the Fretboard Validator I'm going to have. I'm going to have a Fretboard Validator class. It's going to take some form of MIDI input because that's what my algorithm needs. Or it's going to, sorry, not input, it's the tuning of the neck is what it's going to need. It's going to need the number of notes on the neck. It's going to need the actual input that we're checking to see if it has, maybe like 50 and 55. Those are two open strings on the regular E guitar tuning neck, all right? And then it's going to have some member functions. Maybe we want it to know if it's got like a specific played fret, so to speak. Something that's like, we know we want the fourth string to have like the open fret played. And then same thing for the next one. Maybe we know we want the third fret, or the third string, the 0th fret, to actually be playing. Those are two examples of like, it's really obvious what we're looking for and what we expect it to have. Okay, this is what's known as the builder pattern. So let's talk about where we have seen this builder pattern before if we've done some stuff with the Juice framework. Let me pull up these docs again. Now we have seen the builder pattern used in the Juice in a couple places. Probably one of the earliest ones that you'll see when you're doing GUI work is in the rectangle class. So all of these functions down here that return a rectangle are instances of the builder pattern. Like if you say, I want a rectangle with, it's got this bottom Y position and it's got this particular center and it's got this height, that sort of thing. That's the builder pattern in action right there. Another instance of that is the point class. Anytime you see a function that returns returns by reference or returns by copy, it's the same situation right here. Like this point transformed by some affine transform. So you could, you could do a point that you're transforming via an affine transform rotation, followed by an affine transform translation, followed by, something else. That's an instance of where you can kind of sequence the affine transforms. Yeah, here's a perfect instance. All of these are, they are all instances of the builder pattern where you can just chain a bunch of affine transforms back and forth. Okay. If you've ever done anything with the flex item class when you're working with Flexbox, that's an instance of the builder pattern. All of these where if you said, here's my flex item, it's holding my component that holds a bunch of buttons. I've got 4 of them in a row. I'm going to do flex item dot with flex, then however much I want it to flex, and then say I want to have it like a specific width, but flex on the height, or I want it to always have like a specific margin. So I would do flex item dot with flex dot with margin, that sort of thing. And I have an example of that here in Cordy. Let me pull that up. I search for flex item. There's a few of them getting used. Okay, maybe over here in this thing. Yeah, here's a couple right here. Flex item.with flex, flex item.with flex, that sort of thing. Flex item.with flex. I'm not doing anything that involves like with the margin or whatever. Mine are pretty simple. But those are all examples of the builder pattern. And then finally, the last place where we have seen the builder pattern, if you've ever done any menus with the new member functions they added to the pop-up menu item class, these are also instances of the builder pattern. So you can define a menu item and you can specify if it's ticked, if it's enabled, and if it has an action, and if it has a custom component. And it's going to use the builder pattern to basically set all the attributes that are used on this. All right, so I have an example of that here. Set ticked, I think is what it is. Let's see, yeah, over here. So I've got a pop-up menu right here that you set the ID on it, and then you set the custom component for it, and then you set the action that happens when you click on that item. Let's see if I have another one. Set custom component. I know that's used here. Let's see. Yeah, that's used in my tuner. So whenever I click on this thing, this one, I'm doing these, I'm not chaining these. I could be chaining these, but I needed to have a separator in my menu, so I decided not to. But this is another instance where I've got all these things that set this stuff using the builder pattern. That's over here. Calling all of these set enabled, set action, set custom component, set ID, like that. That's the menu when I right click on this and I see this stuff right here. Those are all the custom components that you see right here to your menu choice right there. Okay, so we're getting a little bit off on a tangent. So this is what's known as the builder pattern, and it's where you can chain member function calls and you can modify either the same instance of a class or a copy of that instance when you call those member functions. So for example, the rectangle class uses the copy approach. We already showed that. The pop-up menu item class modifies the same instance. Each of these functions returns a reference to this item right here. Okay, this is all the builder pattern stuff that's going on. So as I said, this is for the fretboard feature right here. We're going to create a validator that validates this input, and we're going to use it. We're going to make our test use the builder pattern. So let's turn this stuff off for right now, and we can go look at some validator data types, because that's the next thing we have to think about is what is our validator going to validate, and does it have access to it? All right, so let's take a look at one of these data types that this validator is going to work with. Now, if you have never played guitar, let me give you a quick gist of how I am programmatically describing how the guitar neck works. So let's go over here. We're gonna go, let's see, we're gonna look at this. So each string on a guitar is tuned to a particular MIDI note. So if I right click on here, I can see that this low E string is tuned to MIDI note 40 right now. And if I were to play on the second fret right here, that's going to be MIDI note 42 because it's, 40, 41, 42, it's the second fret like that. Now I can express that played note with an object like this, my played fret object, okay? This thing has two members in it. Right there, it's got one which indicates which string in my played strings array was being played. And then the other one is for the fret that was being played like that. If we pull this back up, if I've got this note turned on, my string num for this MIDI note 42 might be the 0th index in my played strings array if I'm making the lowest string be the first element in that array. Or if I'm making the highest element be the first element, then for a regular 6-string fretboard, this low E might be the last element or index 5, okay? So if we go back to our example of this thing right here, we can say that this with function right here is going to be passed one of these played fret objects, okay? So that's the background for this particular use case, as well as the data format that my use case is going to be interacting with, okay? So let's take a look real quick at how these unit tests actually work. We'll go back to our documentation, pull this up, unit test. All right, so we're looking at the documentation for the unit test class. The way these tests usually work is that you're going to have some member function in your validator test that returns a Boolean. And the reason for that is because there's this void expect function right here, which wants a Boolean value passed into it, okay? Now you may accomplish this with a regular member function. If we look over here, we might have a member function that's just like called isValid. And all it does is return true or false based on some state here. Or we might use a user-defined conversion function. And for this particular case, I'm going to go with the user-defined conversion function. And that's because I want all of the member functions to return an instance of this validator so that I can continue to chain for a really long time. So the validator's operator bool will return true or false accordingly whenever we pass an instance of this validator to this expect function, okay? So what this is gonna do is it's gonna let me construct and chain the test right inside the unit test expect function, which wants a Boolean. That's enough background for how the tests actually work. And if we needed to test something other than a Boolean, there's a few other member functions. There's the expect equals, like say we wanted it to check whether or not our lowest fret that was produced by the fretboard was 2, that sort of thing, as opposed to, if I turn this up, if I do that note, we can see that like the lowest fret here is 2, but what if we were like, we want to make sure that we don't have any fretboards that are produced below this fret number 7 right there. You know, say we're replicating a capo or something. We could use this expect equals, you know, like expect the lowest fret that's produced should only be 7, and then we check whether or not that's actually the case, okay? All right, let's get started writing this validator over here. I'm going to be doing this at the bottom of the GUI class for my fretboard module. And just to keep the code really clean, I'm going to write 2 macros for making a namespace to keep everything separate from my actual fretboard class. And also block Xcode from automatically indenting, which is a super annoying thing that it does with namespaces. And I don't want to waste time running Clang format to remove that. Okay, so let me write those first. So we're going to do it over here. We're going to do define begin namespace, n, like that. And we'll do another one for ending it. All right, end name space. Just needs a closing curly brace like that. All right, now we can use it. Begin namespace, unit test tutorial, and then we'll end namespace like that. All right, so this guy can go on right here. And now I'm gonna get all my code in here without it being indented, and it's still gonna be part of this unit test tutorial namespace. So that's cool. All right, let's define the interface of our validator to begin with. So we'll do struct fretboard validator. Now we're gonna pass it the tuning and the played notes expressed as MIDI notes. For right now, I'm going to ignore the number of frets on the neck, since this is just a simplified version of my actual use case. So let's add a constructor that does that. And we want std vector int t for tuning, and then one more, std vector int I for input. All right, so let's flush out this with function, and we'll give it a generic mock-up of this played fret thing. We'll add one right here. Struct played fret, and we'll just do int string equals -1, and then int fret equals -1 like that. Okay. So now we can work on what our with function is going to do. We know that it's going to take a played fret, so we'll just do void for right now. And we wanted to have one of these played fret things. Now, returning void won't let us chain calls. So we need to return a fretboard validator. But before we do that, we need to think about how we want that conversion function to actually do the work. And it would be best if it just returned some yes or no state that we pre-computed, as opposed to making it check something inside the conversion function directly. So something like this might work pretty well. Operator bool const, and then we'll just return is valid. All right. Then the issue becomes, where do we toggle this is valid? And as long as we have an instance of this fretboard validator properly constructed, we can call member functions on it without needing to explicitly give it a name. So that's what we were doing here with this pseudocode. If we get rid of all this stuff, we can see that we've just got fretboard validator, some set of arguments, and then with like that. All right. So that's what we want to do. So let's give it a private member variable. Bool is valid, and we'll just assume that it's true by default. All right, so now we can make our with function change this if the output produced by the algorithm does not have the played fret that we're looking for. So the first thing we'll do we've got our default value. The next thing we will do is we will return by reference to enable chaining. So change that, Fretboard Validator. All right. And now we can set up some logic for this guy. Give ourselves a little bit of room. So the first thing we'll do is let's just do some kind of check. So if is valid, and if it's valid and some check returns true, then we can just return our instance. Otherwise, we need to issue a warning that it doesn't have that thing. Maybe we'll add a jassert false and some kind of debug message to ourselves, and then we'll change this is valid flag accordingly. So we will do std cout, whoops, played fret not found in solution, something like that. Let's give ourselves a jassert false, and then now let's flip the flag. Is valid equals false, and now we can return this again. Return this like that. All right, so let's add some members to store the tuning and the input. So we'll just copy these guys directly, and we'll just give it some names. Tuning input to check. All right, so now that we have now that we have this basically set up, let's configure this constructor. So let's initialize our members. So we will do tuning t and input to check I. Oh, and this needs that colon after it. All right, let's think about this verify function that we're gonna put together right here, this part right here. Let's think about this thing. So on a guitar neck, you can play a single set of notes in a few different places on the neck. Let me just turn on the B and the G like this, okay? These two notes can be played like right there. It can be played this way. It can be played this way. It can be played that way. All of these are valid, playable ways that you can play this G and this B at the same time on the neck, okay? So that means for a given set of tuning and played inputs, there are going to be a few possible fretboards that encompass some or all of the notes that were passed in. And this is what my algorithm produces. It computes those solutions, as I'm calling them. I consider this pair of, this set of played frets to be one solution. I consider this set of played frets to be another solution. Same for right here. These are all different solutions for the input that was given to it. Okay, so I need this unit test to verify that the algorithm keeps producing that same set of solutions for the inputs that I know I should always have for a specific fingering. So another example of this would be an E sus 4 chord. So there we go. Let me go back to the top choice. I'm on choice number 1. Okay. If I pass in this set of notes right here, the E, A, B, E, I should always get a correct E sus 4 fretboard back with all 4 notes played at these specific positions on the neck. Okay, and since this is always going to have multiple solutions, meaning that I don't have to play all of these notes right there for it to be considered a match. Like this is just like a regular E power chord. Right, there's E and then the B. I'm leaving out the A. Okay, now the A is being played right there. Okay, that means that I need to check all of the solutions that are returned to make sure that the fret that I'm looking for actually exists, okay? So this is starting to sound like an array of fretboard solutions is what's going to be returned from the algorithm, and that's what we're gonna make next. I'm not going to bore you with the details of my actual algorithm or how I represent the fretboard internally in my program, but I will write some dummy class that kind of does the same thing for the purpose of this video. All right, so let's do that next. Let me turn this stuff off. All right, so let's put together a dummy class that kind of does what the main algorithm actually spits out. Let's define what a solution is. So we'll do using solution equals std vector of played frets like that, and then we can say that we've got a static function. Let's see, we've got a static function that spits out a vector of these solutions. So that way, that's going to provide, if I pull this back up, play those notes, that's going to provide this set of 47 choices, so to speak. All right, I'm not going to do that for the purpose of this video, but it's just to show that our solution set, would be a vector of that. So we would do using solution set equals std vector of solution, like that. And now we can do a static solution set, and then it's a make function, and it's gonna take an input and a tuning. So we'll do tuning and then input, tuning, input, like that. Now, as I said, this is just a dummy function for right now. I'm not gonna have it actually produce that stuff, but let's just write what it's supposed to do anyway. Let's put it outside here. Let's see, fretboard solution set, fretboard make. Oops, yeah, give me the autocomplete. Now for this, we'll just make it return a real boring E major chord in the standard E tuning. So for that, we'll just do, we'll do low string to high string in our array. So first, let's provide the base vector that it's gonna return. So return, here we've got our regular vector. And then inside of this, we've got this vector of played frets that it's gonna return. And let's define that. Okay, so let's make some played frets based on this thing right here. We can do played fret like this. We're gonna have 6 of these because it's a 6-string guitar. And the 0th string, the 1st string, 2nd string, 3rd string, 4th string, 5th string, and a comma. And now we can say that for the 0th string, we are assuming that 0 is this low E right here. So that's gonna be the 0th fret. We can say that the B string is going to be the 2nd fret. We can say that the next note, the next E, is gonna be on the D string. So that's the 2nd index in our string thing, in our string vector. And it's gonna be the 2nd fret. All right, and then now for our G sharp is gonna be in the 1st fret. And then for these other guys, they're just open strings like that. Okay, cool. So this is our dummy make function. This is, we pass in some input and some tuning, and this is the result of that. It's just a single vector that we're dealing with. Okay, so that's our dummy make function. Let's do something with the result of that. Let's store it because we're gonna need some solutions to compare against inside this with function right here. Let's add a member variable right here. We can do fretboard solution set, solutions, like that. And now we can compute that here. Solutions equals fretboard, and we can pass it our tuning and our input to check. All right, so now we've got this computed, and now we can do the check right here. Let's start by calling that verifier function. We'll just add that here as like a little placeholder. We can say if it's valid and verify like that, then we know we're cool. All right, so let's flush out what this verify is gonna do. Bool verify, and it'll be the same thing we have here, passing in a played fret, like that. Now the easiest thing to do is just loop through the vector and then loop through the internal vector and see if the played fret that we're passing in, this guy right here, matches one of these, okay? So we'll just do that. Let's go down here and add our verify function. Bool fretboard validator, verify, and this we're just gonna do for const auto fretboard, not fretboard, fretboard solutions. This we're gonna do for const auto played fret fretboard. All right, if our played fret matches the PF that we're passing in, then we're good to go. But if we try to do that right now, if PF equals played fret, we kill this and try to build it, return true, return false. We'll get an error because this function doesn't exist yet. Yep, invalid operands to binary expression. So we need to declare an overloaded operator Boolean comparison in our played fret. Bool operator comparison, const played fret, other const, like that. All right, we've got this declared. All we need to do is just implement it, which is super easy to do. Let's put that outside. Bool played fret operator comparison, like that. And let's help ourselves by adding some debug information. Okay, so we'll do stdc out this, and we'll just say what this is. String, oops, comma, fret, brackets right there. All right, and close the curly brace off. And we'll copy this and do it for the other one. Other other.string, other.fret. All right, so now we get a little bit of information about what's being compared, and we can compare them and return the result. So return string equals other.string, whoops, and fret equals other.fret. All right, so now we can successfully compare this one, or whichever one we create, with these guys, okay? So now that we've got this, if we build it, that error will go away. Okay, great. All right, we've got our verifier in place, our validator class in place. So let's write a dummy unit test expect and try it out. All right, let's write a bool expect, bool expression. We'll do the same thing here, if expression, then we can do std cout, good to go, and return true. std cout failed test, and std and L like that, and return false. All right, this could potentially return void, but now we can write a run test function. So void run test. I will put this run test inside of here as a public static, so that way we can call it from the main. So static run test, like that. Oh, this should be void, sorry. Okay, void fretboard view run test. Yeah, that's the class, fretboard view. Okay, cool. All right, so we can declare an instance of this fretboard validator, and we can start using the with function, and we can see if all this stuff is cool. So let's do that right now. Let's just do a quick build, make sure that we don't have any weird errors going on. We should be good to go. Should be able to start writing this test. Cannot define or redeclare because, this needs to be outside the namespace. Okay, there we go. All right, great. So unit test tutorial, fretboard validator, and we'll do one not as a temporary, and then we'll do one as a temporary. So here's the named instance of our class, candidate. And let's see, what input did this need? This needed tuning and then input. So we'll supply that. Let's see, we want our regular E tuning for a regular E guitar. So 40, 45, 50, 55, 59, 64. All right, and then our input is going to be 50 and 55. That's going to be, let's see, E, D, G, and B. Oh, this should be 50. Okay, that's our input. All right, so now we can do unit test tutorial expect, and we can do candidate dot width, and now we can define some played frets dot width. We'll check for 2. Oh, I have to provide this first. Okay, so let's see. Let's do it with 2 known good ones. We know that 3 and 1 is going to be a good one, so we'll provide that. Whoops, we'll just do it that way. And then we'll do it again with, and let's do another one. Let's do 2 and 2. All right, and we'll put these on separate lines so it's easy to look at. Let's run this guy so we can see it in action. We'll go to, let's add a jassert false at the end so that way it stops. It pauses so we can make sure that the output we see here is cool. We'll do that in main.cpp, go up to my constructor. A lot of code right here. We'll do this right in the constructor. Let's just include this guy right here. Include, that's not the folder. Modules, fretboard view.h, so I can get to that static one. And we want fretboard view run test like that. Okay, let's go back to our fretboard view. Where's that header file? Here we go. Okay, so if we add a breakpoint here, we'll see this get called and run. So we can step over this stuff. And I'm really doing this just to show what's going on. So here as it's calling the with function. We can see it's going to step into all this stuff. It's going to go through all this. You can see if it's in there. Is it in there? It's not in there. Oh, you know what? I'm forgetting a new line at the end of this thing. Let me add that and get this running again. std cout, std end L, end line. All right, one more time. All right, step on over that. We can see it compared to all these guys. Let's see it compare 2 and 2 with the other ones. All right, that worked out. So now we can jump into the expect. You can see here it's invoking that Boolean conversion function. If we inspect here, we can see that isValid is still true. So if we step out, step in, we're in here, we can see that our expression is true. So it's going to print this out. So step on over that, step over that, good to go. Cool. All right. Let's write one more that doesn't use it as a temporary. So we can go back to this thing that we had before where we just declared it right inside the expect function. We said we wanted to be able to do that. All right, so we'll kill that. We'll do one of these here. We'll just write unit test tutorial expect. And now we can do unit test tutorial fretboard validator. Same input. All right, and then on a new line, we can do with. And we'll do it with another known good one. We'll do this one right here. We know that should be in there. And we'll do it with one that we know will not be there. We'll do, let's see, what choices do we have? We could do 0 and 1 or 4 and 1 or 4 and 10 or something like that. Let's do 4 and 1. So we know it's definitely not there. Let me extend this a little bit. And we'll run this one more time. Again, we know that this one obviously does not exist in the input. And we'll just step over all this stuff. You don't have to do it with breakpoints. I can just click that and push play. And you can see that like it did the right thing. It said, hey, this one's not found, the one that they're looking for. 4 and 1, that's what they were looking for. It does not exist in this. If I wanted to, I could add some kind of like played fret member function that actually prints out which fret is being tested. Because there's no way to tell based on this which one is being tested other than just being like, oh, it must be the one on the left because that's the one that's being used all the time. All right, so we'll step over this JSR false. Let's get out of here. Step out. There's our with function being called. All right, we'll step in again. That conversion function gets invoked. We step out of that. It returned false. If we step into the expect, we can see that the expression is false. Step over that. And we failed our test. stdc out, failed test. Okay, very cool. That's an example of, writing a unit test that can validate some algorithm that we have, okay? Now, the next thing to do would be to actually convert this into an actual instance of the, where's that unit test class? Unit test. The next thing to do would be to do that. We make a class that's derived from unit test, and then we make a static instance of it, and then we use the unit test runner to actually do the testing before we run our app. But that's more complicated than what needs to be done for this test, because the instructions are right there in the documentation. This is more of a tutorial in how to actually go about writing the class that gets used in the unit test such that it has a builder pattern syntactic style. Okay, very cool. All right, cool. So you might be asking yourself at this point, how could this apply to actual plugin development? Well, just imagine that you have some function that spits out a waveform, and maybe you're doing a wave shaper or a compressor, and you know that with a given input function, maybe a sine wave or something, and a given gain parameter, your algorithm should spit out a block of samples whose RMS value is always greater than some dB level. But it should never be above some other level, okay? Or if it was in the case of a limiter, you could say that the RMS level should always be below some threshold. It should never go above that. Now, that would be a fairly complicated verifier because you would want to pass it something that takes a lambda. That would be your input function that produces the waveform block. That produces the block of samples that becomes the waveform that you actually run through the validator. And then internally, you would need to perform your DSP computation and then compute the RMS, right? But you might find yourself doing this type of unit testing if you're in a situation where you're porting some Python DSP code to C++, and you need to make sure that your C++ DSP performs the same as your Python DSP. And an offline unit test approach like this would be one approach you could use to make sure your DSP is being ported correctly, okay? So with that said, that wraps up this presentation on unit tests and the builder pattern. If you dug this tutorial and you want more of this type of instruction and whatnot, I have a Juice C++ course that I mentioned at the beginning. I teach it with this mentored one-on-one approach, so if you dug my in-depth explanations here, you're definitely going to dig that course. You can check it out in the link in the description, and you can start the 7-day trial that goes with it. Thank you again so much for watching. If you have any questions, feel free to message me in the Audio Programmer Discord, or if you happen to take the course, you can just message me in the Slack workspace. You're going to find me under the username MattCatMusic. All right, thank you again so much for watching and tuning in. I will see you in the next video. Deuces.